Hello, good afternoon, everybody. Thank you for joining the Taiwan Semiconductor webinar this afternoon. The agenda is here. It will be the similar format as usual. It's about just some new products and some product updates we have. It will last about, I think, about 3/4 of an hour. Gives you time to ask questions at the end. If you're not feeling comfortable about using the microphone and that type of stuff, you can also use the chat function to ask questions. It's usually difficult if you're presenting to follow the chat functions, but Undine is doing that this afternoon. Also, the presentation is available if you want the presentation, because a lot of people are joining. We may not know you all. Please send an email to Undine to request a copy of the presentation. Now I need to go to slideshow, and then we'll get going. Here we go. I hope you can all see the screen. Should there be problems with the audio, also please alert Undine so she can interrupt me and I can repeat something. So today we're going to talk about new, fast, efficient rectifiers, new lighting ICs, and some general product update slides. We're going to start with the new fast efficient rectifiers. With fast efficient rectifiers, we mean something like less than 75 nanoseconds recovery time. New for us is, and it's going to be somewhat a different webinar today, because we're going to talk about the actually technology to make rectifiers also. Our new rectifiers are called Planar technology. Fast recovery, epitaxial diodes. Sometimes it's not a first name of somebody, it is an abbreviation we use in the industry because we're talking also about epitaxial products. So what we have done actually recently, we're going to introduce a whole line of new products, but we just introduced 16 new products recently. On the left, you can see the part names. They're our own part names. They don't copy somebody else's, but we'll give you some cross-reference information afterwards. The first packages are introduced in some of the newer packages on the market. This is the SOD128 and the SOD123HE. Those are smaller, low-profile packages with flat leads. Of course, the industry standards, we're not forgetting them, SMA and SMC, and the SMPCU, also called the TO277A, is the one with the exposed pad at the bottom, and the U stands for sideward wall flag, so it's aimed at automotive. If we're going to look at the graphs here, or at the table here, I mean, we're having 100 and 200 volt versions and different current ratings. The only thing I would like to point out to you is that the VF is 0.93. If you could please memorize that for some slides afterwards, I think that would be a good number to remember. And the junction temperature, of course, here is 175 degrees C. We go on now. Is actually, this is the issue is, or one of the issue is that it's not so easy to sell this product without knowing the technology. Our new part is the PU3D. Our existing part is the EHH3. Obviously, sometimes the other part names like ES3, ES1, ES2, those are the ones that everybody uses in the industry, and they're even more popular, but those are rated at 175 degrees C. Now, if you look at the comparison of the data sheets, you'd say here, what's the problem here, or what's so special about here? And the answer is not much. The difference of 20 millivolt, and we'll put that in perspective on the next slide, is not that such a significant advantage. The 2 or 5 microamp specs in the data sheet, as usual with rectifiers, are not really representative for the actual performance in the rectifier device. So if you actually go and see at the next slide, and we're going to compare the averages, what we're seeing here is that actually the average of 0.811 or 811 millivolts or 805 millivolts, that's on the first line at 1.5 amp. Actually, you can see that the existing device is even slightly better. So there actually is, if you are a user of this product, actually you would say, hey, what's in it for me? There's no difference. If you go to the bottom line, we can say that it has a lower leakage current, but frankly speaking, 4 nanoamps is lower than 10 nanoamps, but it's really also peanuts. It's really not that much. So the data sheets of these devices are not that different, or the actual performance an engineer sees are not that different. We can look now at 125 degrees C, and if we're going to look at this here, I suggest we go straight to the bottom line, because actually the first line is a similar story at 225 degrees C. And if we go to the bottom line, we can see that the planar part, the FRED, is 880 nanoamps and average, and the GPP part is 1.93 microamp. Again, it's double, but frankly speaking, it's not such a big deal. It's not such a thing that a average designer would say, I would like to use this product because of that. The last slide I'm showing on a typical performance here, comparison here of the two parts, is with the TRR, or the recovery time. Here we always see a spec of 25 nanosecond. Here we see an actual performance of 22 nanoseconds or 21 nanoseconds. The reason for showing this slide is that it's a good thing to remember that the TRR, or the recovery time of a device, has a positive temperature coefficient. You don't see that mentioned very often, and people sometimes forget this, but actually the recovery time of a rectifier has a positive temperature coefficient. In the meantime, we've also have on our website also explanation notes, application notes, explaining all the parameters of diodes which you can find. The new data sheets in the planar device will also have values for things like QRR or the peak reverse current, IRRM, to give you more, or the designers more of a feeling about how these the recovery slope and shape looks like of these devices. What you see on the left here, the test condition, is typically how we test those devices. All our high volume test equipment is made this way. And that's why we have this condition of a forward current of 500 milliamps and reverse current of 1 amp. A lot of the real applications in the world are, the devices switched off with a certain slope of 50 amp, 100 amps, and 200 amp per microsecond. In the meantime, our data sheets of these new devices also include information about these recovery times under these more realistic conditions. They are usually given as typical values because all the testing is done on these mass production test equipment, just to make sure that we 100% test the recovery time of the devices. So here you are. You need to go and sell this. Now, this is not so easy to sell as a sales guy, right? We're looking at planar and we're looking at GPP. By the way, GPP stands for glass passivated pellet. That's how it was called 30 years ago. And that's where the process comes from. Now, we'll talk a little bit, we'll have a comparison slide next, on the next slide, we'll list the difference between this, but let's look at this visually. The GPP process is an older process. I think only triacs are still made using GPPs and rectifiers, and I think also some thyristors, maybe the smaller ones. So, but other processes for discretes tend to be all planar, which is a standard diffusion technique. This GPP one, what happens is it actually, we call what we say, we etch a moat, or that's a moat is something you have around the castle, and that's the best way of looking at this GPP slide. So there's a big, ditch next to the diode, and we put glass in there. So this is actually a very cost-efficient process. It's very good. But of course, what it does is it wastes quite a bit of space on the IC. So you see that, on the left hand and the right hand side, we maybe you lose 15 to 20% of space on the IC. On the left hand side, the planar devices are all other discretes are made. Some of them, of course, with trenches have slightly more complex processes, but the structure of the device is similar, where the two yellow half circles on the left-hand side and the right-hand side, those two circles are what we call the passivation structures, where the reverse field sometimes also is terminated. So this process, planar process that we use to the new ICs, to the new rectifiers, sorry, is slightly more advanced, although it's also not new. It's also a long time already in the business, whereas the GPP process is the more cost-efficient process. The other on the bottom slide, what you see there, you might see on the right-hand bottom side, you see these two red arrows squeezing there and that type of stuff. That means those moats, or those, you know, what we dig around the IC, around the, not the IC, the rectifier, are kind of like quite deep, so it's easy to break those wafers. So that's actually gives you an overview of the differences in structure. Now, who's interested in that? I mean, it's fair to say that the majority of our customers just look at the data sheet and not at the technology behind it. So that is something you know, we acknowledge and we know, and that's fair enough. But you know, we still have customers specifically, or maybe not knowing that they need planar, or not knowing why they need planar. So let's look a little bit more at the comparison. I'm just showing you one slide about this GPP process, and to give you an idea actually why it is so cost effective. Actually, it actually only has 3 masks or 3 lithographic steps, as we call it, sometimes to do to describe the complexity. Actually, later on, we're going to talk about some lighting ICs, and those lighting ICs actually have 25 different lithographic steps. So that's a different world, and so we are living in a different world. So what we are doing with the GPP, or the glass passivated pellet process, is that at one stage, and this is the second photo which I highlighted there, is we're opening up the device and we're applying glass to that. There are many ways to apply this glass, and also many ways to grow the oxide. So that's why there are also many different variations of doing that. But this gives you an idea how the GPP process works, how simple it is, and also why maybe if you are a professional auditor that walks around 8-inch or 12-inch fabs every day, that you may not be impressed by this process. But it's very efficient. Not only we make several billion rectifiers a month, but you know, other companies do so too. And you know, you can easily say that more than 100 billion, if not hundreds of billions of rectifiers are in the field using this process. So here we are comparing the planar and the GPP process in one slide. So this is the GPP process, is long already out there. Rectifiers are low in any Pareto analysis of field failure. So rectifiers usually don't show up very often in a field failure in a power supply or a device. You know, if they are adequately rated by, let's say, 20%, and you don't push the junction temperature to the limit, you're probably okay with the rectifiers, and you won't see that many field failures. They're cost efficient, they're long established, and you know, there are different junction TJ ratings. When we say different ratings on GPP, it either means 150 or 175 degrees C. The difference is, you know, there are different ways in sawing the die, different ways of making oxides and that type of stuff. So actually, the GPP process meets most demands. Planar process is more automated. It may appeal to automotive auditors, so that's why we also call these planar diodes sometimes optimized for automotive, because they are the people that, you know, run around all the wafer fabs in the world and compare processes. So that's why they sometimes prefer the planar processes in this case. It also has other advantages. This GPP process is limited to 1,000 volts, really, in practical terms. So this will, you know, the planar process will be able to make higher voltages. And when we say lower leakage current, sometimes what we call a diode is round or soft, when the curve for the diode where it breaks down is not so sharp. A planar process is actually more sharp, and so it has higher avalanche capability and also potentially ion implantation. It makes a difference. So this actually is the overview of the two different processes here. When we're going to produce our newsletter on this product, which is on the way. We're going to have a cross-reference here. And let's talk a little bit about the people we're seeing here. So Vishay actually would have 95% of their products just like us in GBP. The products you're seeing here is more the stuff they bought from when they acquired International Rectifiers. So this is more this type of product that you're seeing here, not their traditional ES1s. Nexperia is another story. Nexperia is pure planar on 8-inch. So Nexperia is also the people that occasionally make a lot of noise about planar diodes in GBP. So those are the people that, if customers absolutely insist on it, then we can second source them and we can go after their business. If customers say that an Nexperia says mean things about GBP, then we should also be capable of reacting. Rome is another company that is actually tends to be predominantly on planar diodes. So the rest of the business, like us, Vishay, Panjit, those people tend to be, all the people in Taiwan and China tend to be on GBP processes. Let's talk of the favorite one in Europe here, or one that is actually doing a lot of business here in Europe. And I made a summary of all their planar diodes rated 175 degrees C. They've got them in all packages, and of course we're crossing them now, or we're offering them in more like the smaller package, like the SMA, or on the fifth line, the SOD 1, 2, 3 flat, or those type of products here. What I wanted to point out to you while we're looking at this table is the VF. The VF of ST tends to be 0.95 to 1.5, or even a little bit higher, 1.1, some of these diodes. So as you can see, we can not only go after ST with crosses on and offer 175 degrees C rated products, but actually we can also probably improve on the spec and on the efficiency of the device. So actually ST is certainly a business we would like to go after with these planar diodes. And ST makes planar diodes since 30 years. That was their specialty. When they came on the market, they always had a planar process. The other one, which was not mentioned in our official cross-selection guide, is ONSEMI. ONSEMI is a different case because they have a lot of diodes which they also acquired from Fairchild, and Fairchild used to be more GBP, and ONSEMI had some planar products. So this is actually so sometimes a more difficult situation to offer crosses here and what is correct to do or not. ONSEMI also, you can't select the devices by TJ here. The only thing I would like to point out to you here also with ONSEMI is that a lot of these diodes, and we do have equivalents for them, have a very good spec on the VF. So the 0.875, which you see 3 or 4 times repeated in the column of the VFM max, is sometimes difficult to meet. We can do that too. The reason, or how you can do this, the trick is very simple. To obtain a fast recovery time of, let's say, 25 nanoseconds, you need to add platinum to the device. That's one of the process steps. If you add more platinum, the VF goes up. If you add less platinum, the VF doesn't go up. And as a result, a 35 nanosecond diode may have a better VF than a 25 nanosecond diode. So this is some of the background of ONSEMI, where there is a mixture of GBP and planar products. So this is an overview of where we're going. We already introduced 16. We are going to introduce a few more in the next couple of months. I highlighted 2 there. That's the 6 amp in SMB and SMC. So one of the things, if you visualize again this picture of the planar device, is with all the sometimes the waste on the left hand and the right hand side, where you lose some of the active area. The planar die is a more complex and more expensive process, but you can get the same result, of course, with a smaller chip area. So that is one of the advantages also of planar. So what you can do is, of course, you can push or squeeze more power out of an existing package. So for the SMB and SMC package, you can actually go up to 6 amps with a 940 millivolt spec, which is actually pretty good. So that is one of the technical advantages of the planar, is that We call that sometimes not just the chip size, but the active area. And on GPP, not all the area of the chip is used, and some of it is lost. So that is, where Planar has another advantage, and that we're going to squeeze out in the next couple of months. We're going to have those 6 amp diodes available. And then, as a summary, we have the key advantages of our upcoming FRED product line. Complete 100 and 200 volt product lineup with 175° C qualification. Improved power density versus the current GPP product line. What we mean by that is that we can get 6 amp, for example, out of an SMP or SMC package, and we have the lower leakage current, a nice, with a nice edge at the breakdown, and of course we have a very fast TRR of 25 nanoseconds. So this is our recent expansions to our fast, efficient diodes, and we spent some more time on this because it's not so easy to sell without having a background on the technology behind those diodes. The next step is some of our lighting ICs. We've introduced 2 new lighting ICs, one a couple of months ago. The press release will go out somewhere this week. Just been reading it 5 minutes ago. One is actually also quite recent. But before we go there, I'm going to give you a product 3 of our preferred devices, which you can then, if you get the presentation, use at your customer here. So we're going to talk about 2 devices here. One is the buck converter, which you of course find on the DC-DC version of the product 3, and one is the bottom one of the linear products, which is DS19605, which is automotive. What you see here is our preferred devices. Historically, we've been making AC to DC converters. These are our preferred devices. We've got one in case of isolation, the other one a non-isolation. As you see in the title, we specify this. They're all aimed at single stage applications, and they're all primary side controlled PSR. And the other products here we've introduced in the market is the buck boost converter, SEPIC, and also the boost converter, which we also have non-automotive versions. Let's go to the 2 ones we're highlighting here are fairly new, the TS19503 and the TS19605. Here, and this is what we're highlighting here, this part is also good for non-automotive applications. So this is something we want to highlight here in the first slide. And actually what I put in red here is what is typically automotive. Now, it doesn't harm if a device is ACQ100 qualified, so that is an advantage for everybody here. So it's a buck converter. I'll leave the title first before I go into the details. 2 amp, it's a lot for an LED, but it's got a 200 milliohm on-chip resistor. On-chip MOSFET on there. It's a step-down converter or buck converter with integrated FET, of course. Then it uses high side current sensing, and you can dim using PWM and analog capability doing it. So what happened is, you can see that the most important features of the device are it's an M-sub-10. It's ACQ1 qualified, and of course, what makes it typically automotive is it is used on a 75 volt process, which is actually overkill. For low dump, you made 40 or 60 volt, depending on your car or truck, and the 75 volt maybe not be enough for a 48 volt environment. But still, the 75 volt helps us in non-automotive applications where you can then control large strings. The hysteretic control will come up a little bit more on one slide. I've learned today that Americans call hysteretic control bang control. That is maybe another part name or another name you need for that. What actually it does is it reduces the EMI of the device, or the immediate EMI. So we already mentioned the 200 milliohm internal FET, 2 amp output capability with high efficiency, obviously depending on the input-output relationships. Typical 2% LED accuracy. And then, of course, the 1000 to 1 dimming factor is not small. So that is not small is actually what I should say, how I should say it is actually pretty good. The brightness pin is, we're going to look a little bit at the dimming profiles a little bit later on, but actually if you put a 0 on the dim pin, you can actually turn off the device also. The switching frequency is 1 megahertz, and actually what is then typically automotive or the high current sense is used also in automotive is, of course, there's a fault pin that actually the device not only measures the typical fault conditions, which is also including faulty LEDs in the circuits, but it also has a pin to actually give feedback to the controller that does it. So let's go and look at it for non-automotive applications. If you're, just to give it a broad appeal to distributors. A lot of these people use a two-stage design versus, as you can tell on our overview, we have a lot of single-stage ICs, but we understand that a lot of people actually use a voltage rail in the meantime and convert to a constant current afterwards, after rectifying a voltage. So that device is actually very good for that because it can supply this constant current using a 75 volt CMOS process. What that actually means in practical is that it can drive long LED strings. You can add 15, 20 LEDs to this device and can still drive it with one IC. So this is the advantage of the high voltage CMOS process. And then, of course, it gives you design flexibility. You can do one LED driver and actually add a variety of loads, to produce a variety of lumens with one single design. I think the most important slide that was also already in the first slide, some people might have already noticed it, but it's kind of more fun if you look at it this way, is that here you have a 500 milliamp, you're driving a 500 milliamp LED string or LED string. You're varying your input voltage and of course, depending on the load of the amount of LEDs. So you can actually see the versatility of the device here. You can control 15 LEDs up to down to one LED, because we had one customer who specifically asked us to measure the performance of the device if you put 60 volts in there and input voltage and one LED. And it does work. It depends, of course, on the duty cycles. So the PWM dimming, the 1000 to 1 factor is there. So that works actually fairly well. I just wanted to show the linear dimming there, so you are aware of linear dimming curves also. And this is not 100% linear because you're actually at the 0 voltage. You actually turn off the device. The device has all kinds of other features typical for analog ICs. It uses, you can use a varistor on the dim pin to compensate or control or minimize the LED temperature and reduce the current if the LED temperature goes up too much. So there are a lot of other features usually associated with this device. The last slide I would like to take is of course, it makes it a little bit, looks a little bit complex, but actually it is in the data sheet here. This is the EMI test results using automotive CISPR standards, and we actually meet with a relative margin and a relatively simple EMI circuits to meet these automotive norms. And that's done by the hysteretic control, which is a very simple control scheme aimed at optimizing or reducing the EMI. So that is also an essential part, which we actually wanted to mention to you. And more information is available on our website on this. Calculation examples can be done via spreadsheets. We've also made a small video where you can look a little bit more at the details of the device, and further support materials are available on how the dimming and other functions of the device work. So there is more support material available on this device. The second one, which we are actually showing now, is which is actually quite recent. It's from 2 weeks ago or something like that, is a 3-channel linear LED driver with analog and PWM dimming, which is ACQ100 qualified. So I'm going to read more or less. This is the newsletter which was just released on our website. So it's a 3-channel LED driver, analog PWM dimming. The target is automotive lighting applications, but there are obviously some other applications too where it could be used. They're high side drivers, typically for automotive. They can go up to 150 milliamp per channel. That's obviously a lot, but the device will get rather hot there. But we use a trick, and that is you can cascade external PNP transistors to reach up to 400 milliamp per channel. Or you can use those external PNP transistors also to reduce the temperature. Again, it's made in a 70-volt process. It has a low quiescent current, which you would typically require for automotive applications. And it has a lot of features when it comes to protection. I'll talk a little bit more about them because everybody has their own way of doing it. You expect, of course, under voltage lockout and some of the other ones, but it does monitor the LED string and can detect faulty, wrong LEDs. So that is one of the features it has, and it has also, I think the bottom line is the most essential part is it has diagnostic features to meet automotive requirements. So it can really give feedback to the microprocessor or whatever device it actually communicates with. One slide overview here. I put some things here which are typical for the device here, or where it differs a little bit. If you go and look at a little bit at the schematic there, you see on the top side there are current sources, two current sources driving 3 LED strings in parallel. So that's where the top on the top right on the IC pin out on the top right hand side, those 6 pins are doing. On the bottom 3 pins on the right hand side, just mention of course the measure, of course, just the current through the string via voltage, and then make sure that the current is controlled and also the current in between the strings is controlled. You can, each channel, has a separate PWM or analog input. You can set the current via the IZ pin. Default FLT and FLTS flags are a little bit different, and here they are similar to TI. So we've got a couple of TI devices here. We'll mention later on and things like that. So the way you give the fault diagnostics back to whatever device it interfaces with is done in a similar way to Texas Instruments. So that's something I'll mention the part names of TI later on in detail. And the part obviously has an enable part also that you would expect from a automotive device, so you can put in shutdown. So it's ASCQ 100 qualified. Again, we mentioned a 70 volt here. That's very high voltage for the process. 150 milliamp per channel. That's already a lot. So what you can see is that also with external extra power, we can give up to 200 or 400 milliamp. So people may not choose to use it, these linear drivers, up to those high currents because of temperature concerns. But in that case, we can also make some proposals there on how to reduce the temperature. So the dimming function is also mentioned, PWM or analog. I think we've already mentioned that. But VREF pin there, that's the third thing I circled there. And that's the pin here that's going to drive the external elements to get extra power. And get actually what you want to do is get power out of the device. And the simple way of putting it is, let's say the battery voltage is 12 volt. The LEDs are 9 volts. So there's 3 volts between the battery and the LEDs. And whatever current is, that has to be dissipated in the IC. So we really, if the current goes up, that's a lot, could be potentially a lot of power. And so actually we want tricks to get that power out of the IC. So the diagnostic functionalities are mentioned already before, but LED string open and short is the most important one here. The I set there, that's the thing here where you set the current. So you really want to also make sure that is also controlled. There's a separate fault pin for a single LED short failure, which is also measured and fed back to the device. Talk a little bit more here. Again, a busy slide. Sorry about that, but here in red, what we did here, we went to the device or the block diagram on the left here, on the other slide, and what we're doing here now is we use this VREF pin to actually add 3 transistors. So what's the purpose of these transistors? Actually is to get power out of the device. And even if you're using, let's say, whatever you want to put the VCE voltage here on the device here, you can, if the LEDs are 80 or 100 milliamps or somewhere in that area, you can probably, use even actually fairly cheap bipolar transistors here to get some of the heat out of the device and reduce the junction temperature of the IC itself. And that's the key feature of the device is this VRF pin. We've seen that TI has made a similar concept just recently in December or something like that, where they use more or less resistors to share the power dissipation away from the IC. The rest of the features here are pretty similar to what we've already said here. Here you can see that the accuracies are obviously a little bit better when you go to lower currents like 30 milliamps or that type of stuff. And of course, what you see here is the dimming between the difference in dimming between the three channels is fairly manageable. And on the left-hand side, and what you also see is, of course, a device like this only functions when the reference is stable over temperature, and that is actually what we're proving here on this device. So those are the key features. If we're going on here, if you want to do a little bit more about the product positioning of this device. So it's automotive LED lighting, and it's predominantly the second line here, stop and tail, positioning, fog and turn lights and that types, and also some of the rear lights, you know, especially the rear lights. That's where this is used quite a bit here. It's used especially in in automotive applications. It can be used as general RGB when you have three strings. Of course, you can always use it as an RGB application or white LED driver, and there are other industrial LED applications available here. Product positioning, though, is important. We don't always compete against Elmos. So this is the first time that Taiwan Semiconductor is competing against Elmos. And this is going to be the E5222, 82, 84, 87 is the one that we're going to compete most against, or is one of the top devices we're going to keep most against. They've got three controllers, obviously with different current sinks. That things happen. I think the cost of the current sinks in the overall device is not that high. So I think in this case, one device that we do should actually make it possible. The other competitor, there are other competitors too. Infineon obviously is there. There's no way of not mentioning Infineon. But I think originally the device was closest to the TPS 92630. That is the bottom three of the devices of TI. I think that's the one we were competing with when we had this device in mind. And then we added the function. We started designing this device, I think, about 18 months ago, of getting the heat out of the device, and in the meantime also TI launched the path, and that's the first one, the TPS 92633, that has the automotive 3-channel high side LED driver with thermal sharing. So the thermal sharing is there in that device too. It's done differently from the way we do it. The Infineon devices are 14-pin devices. I've got the impression that they're more captive in their own system and that they're trying to sell maybe the whole system. But these Elmos and TI are definitely two people that we are going to compete with on this device. This device is, doesn't have so much support material, frankly speaking. A linear driver, what can you say about it? Is what our friendly marketing people say, and they are probably right. But obviously, some of these TI data sheets are 50 pages or 40 pages long. So obviously, we can help you with if you should come across TI or Elmos. So you have to get the Elmos data sheet from all data sheet and those sources. So if you come across those companies and you want us to compete with them using our products, please let us know. We'll do our best to help you, but we don't really have like a design program and that type of stuff on it, because it is in the end just a linear driver. Good. That was a general overview of the lighting ICs. The last couple of minutes, we're switching to something completely different, and it's there's nothing new here. What I'm sharing with you is, the last slide has new information. What I am sharing with you is actually just a couple of overview slides, which I liked, which somebody in marketing in our headquarters produced a couple of months ago, or 2 or 3 months ago. And actually, I think you can actually use them in your day-to-day job. So that's why I'm sharing them with you. And here we go, because the small signal market is, it's a busy slide, but it gives it all on one overview. A lot of people would say this is obviously a commodity, and that's fair enough to say that is a commodity. But so we have a bunch of Zeners in all packages. We'll give a little bit more about these packages later on. And then, of course, with using the BZX and BZV and the MMSZ and some of the more familiar part names or groups of part names in the business here that are fairly standardized. And we also have them in a standardized range of packages and things like that. So the 4148, we're really not going to spend that much time on it, but we also have, of course, a fairly large variety of products here. General purpose bipolar transistors, the BCs will always be there. And then, of course, small single Schottky diodes are also available now in more and more packages, because you can also reduce the space of these devices. Small signal Schottkys, MOSFETs, that's another story. We'll have another slide about those. But let's go first and have a look at these packages. A lot of these dies, if you have 100 milliamps and that type of stuff, and the power dissipation really is not that high in these devices. Sometimes you have 10 milliamps maximum, that type of stuff. So a lot of these dies you can just shrink and put in smaller and smaller packages. That's why I actually like this slide. It gives you a good overview. It's a bit busy. This slide, I think, is a little bit more fun to look at. You can see at all these packages here. On the left-hand side, the MELFs are a little bit like the demise of the MELF is a little bit like the apocalypse. It's been announced several times, but they're still around, especially the mini MELFs. They're definitely not new and that type of stuff, but they're not at their end yet, so they're over there. You can see, and then we go to the ceramic packages. Probably, some people like those because of the profiles and that type of stuff. But frankly speaking, there will always be a mismatch between in the temperature coefficient of ceramics and semiconductors, so they'll always have a more limited application space. Let's put it like that. The TO92 is really running on its last legs. That's really going. Then you have a bunch of other actual packages, but the big, all the big packages going from SOD 123 to SOD 923F are of course all included in the product portfolio. You have the gull wings and the flat leads. Wave soldering is certainly not going, so a lot of these things will be wave soldered. So the SOD 23 will be around for a long, long time. And so will things like a SOD 363 and a SOD 323. So we think we have a complete product portfolio lineup here. Obviously, some people would say, hey, you're missing the DFN package, the small square packages. That's correct. We're actually probably going to talk to you about those in a webinar soon, as we are planning and got in the pipeline in our roadmap ESD devices. And if you're in ESD and you have these mega fast data rates, then every millimeter of lead frame is an added inductance and is negative for these devices. So it's not just a space saving on if you're reflow soldering potentially, but also from a technical perspective, it is a reduction in inductance potentially, these DFN packages. So we're coming with them pretty soon, especially for ESD devices. So those are our small signal discrete package overview. I thought it was a nice slide for you to have. So here it is included. And the last slide before we go to the questions session is a crowd pleaser. Let's say a crowd pleaser, as they say. I think the 2N7002 is available, or the market is still huge. It's actually probably small signal MOSFETs are actually several hundred million is the market size for this. These are some of the more popular devices. The dual ones are also common in the measurement circuits and that type of stuff. So these devices, they are, it says in the title, being released. That means that I think when I checked this morning, the data sheets were already on the data sheet, on the website. So I think the official release is on November. So we already decided to include it in this overview webinar because they are very popular devices and especially also distributor and good commodities to have. So that's it from my side at the moment, and that's the end of the webinar. We did our 3 quarters. and so we're finished on time. The rest is either if you have questions, please ask them now. If not, or you can use the chat function to ask them to Andina, who will tell them to me. And the third one is, of course, do not forget to ask Ambina, because I saw a lot of people logged in that didn't have, or that maybe we don't know directly in Munich. So in that case, please make sure to contact Undina, who is on the website, to get a copy of this presentation, which is available for everybody. So we'll open the floor for questions, please. So Ondune, was there anything in the chat box?
Yeah, hi, there is one question from Frank Holobeck. I would like to receive a copy of this. Okay, yeah, sure. No questions in the chat, but you can unmute yourselves to ask your questions directly.
If there are no further questions, then, this is not so uncommon for rectifiers. Let's put it like that. Then I would like to thank you all for your attention and attending this webinar. I wish you success promoting the products of Taiwan Semiconductor. And I hope you found the webinar of interest. And I hope you can join us again soon for other updates. Thank you very much.
Thanks, Jos. Goodbye.
Bye.